By now, we have looked at a couple different ways to interpolate a set of data. First, there was Gregory Newton from the difference tables. Then we introduced Lagrange interpolation and showed that it gave us the same result as Gregory Newton at given values. So why do we have two different ways to do the same thing? To answer that question, one important reason is that we don't always get evenly spaced data. Take the picture on the screen as an example. These data points are spaced evenly in neither the x nor the y direction. As was presented in a previous lesson, Gregory Newton only works on evenly spaced data. Lagrange interpolation, however, can handle uneven spacing. In the next slide, we are going to find a cubic polynomial to interpolate between the 4 points in red. Here I plug in the numbers. This is what the process for that looks like. Feel free to pause the video if you wish to peruse the details of this calculation. What we just saw works well enough, but the large number of calculations to be performed make it likely to make a calculation error, especially if using a handheld calculator. Next, I propose an alternative approach. However, we will see in the following lesson that this is intimately connected with the form of Lagrange interpolation seen here. Given 4 data points, y0, y1, y2, and y3, we can find a third-order polynomial that passes exactly through each one of them. This polynomial is represented by coefficients a, b, c, and d. This amounts to a system of 4 equations and 4 unknowns, which can be solved. Better yet, we can rewrite this system as a 4x4 matrix and use linear algebra to solve for the coefficients a, b, c, and d, whose value is unknown at this point. This slide shows, in symbolic form, that we must invert the 4x4 matrix and multiply by the y vector in order to solve for the coefficients a, b, c, and d. Here I plug in the data from the second slide in this lesson. Go back and verify if you need to. The bottom expression shows the numerical inverse of the 4x4 matrix on top. I used Excel to compute this. I will note in passing that direct matrix inversion is not the best way to solve a system of linear equations, especially if there are many of them. Here we only have 4, so we can get away with it. Given the matrix inverse on the previous screen, we must multiply by the adjacent vector. The following slides use color coordination to show how matrix multiplication is performed, in case you needed a reminder. We must multiply the colored pairs together, red multiplied by red, orange multiplied by orange, yellow by yellow, and green by green. When we add these 4 pairs together, we get the value underlined in blue. In this case, a equals 0.18599. Same thing as before, just that we are in the second row. b equals negative 0.90226. Same pattern for the third row. c equals 1.895079. Lastly, the fourth row. d equals 0.181207. We have done all the work we needed to do. The following step is redundant, but for the sake of a more complete understanding, I want to show you how to check your answer. If I multiply the original matrix by the coefficients we just solved for, what numbers do you expect to get? Well, they should be the y values we pulled from the data table. In the next steps, I go through matrix multiplication similar to before. If this is something you need to practice, please follow along with your own pencil, paper, and calculator to make sure you get the same numbers I do. Once again, we must multiply the colored pairs together, red multiplied by red, orange multiplied by orange, yellow by yellow, and green by green. When we add these 4 pairs together, we get the value underlined in blue. For row 1, this says that y1 should equal 0.459698. Did you get the same answer I did? Secondly, does that value match the original y value from our data table? If not, that is a sign we did something wrong. Same drill for the second row. This says y2 should equal 0.929263. Does that hold true? Third row is the same process. y3 should equal 1.416147. Lastly, y4 should equal 1.801144. Do these values match the original data table? Like I said before, if they don't match, then we did something wrong. They should match, so this is just a way to check our answer. Now back to the main point. We solved for the coefficients, so now we can plug them into the third order polynomial. That should look something like this. Notice that if I evaluate it at x equals 0.2, I get 0.52562. This is the same number I got from Lagrange Interpolation in the beginning of this lesson. Go back and check if you don't believe me. To me, this method of using a 4x4 matrix is a lot more intuitive and much less prone to calculation mistakes. However, I've presented both ways, so you may choose which one you prefer. Regarding linear algebra, I leave another note in passing. The matrix we use to solve for the coefficients of this polynomial is called the Vandermonde matrix. When it is large, there can be a lot of round-off error that makes the subsequent calculations less reliable. For that reason, other methods in linear algebra are better suited to the task of finding coefficients of an interpolation polynomial. One such method involves the use of orthogonal matrices, but we will not discuss that here. Another reason I prefer solving for coefficients of a polynomial is that I only have to do that once for a given range. What if I wanted to know the value at x equals 0.4? Well, I'd have to repeat the tedious process at the beginning of this video. Or, I could simply plug x equals 0.4 into my third order polynomial, which requires far fewer calculations, thereby leaving less room for mistakes. Here I have plotted that third order polynomial in the desired range. Notice that it passes exactly through the 4 y values we input, as seen by the orange dots. This is a must for any interpolating polynomial. It turns out that I pulled the data from a known curve, so we can compare our interpolation to the exact values. The curve I used is called the cycloid. It is produced by a point on the outside of a circle as it rolls along the ground. Here is a simple depiction of how the cycloid curve is constructed. A represents the radius of the circle. In our case, I used a equal to 1. Whereas we can represent the cycloid in terms of x as a function of y, we cannot represent it, in closed form at least, in terms of y as a function of x. Sometimes it might not be possible to express either. This is where the power of a parametric representation comes in. Two parametric equations are shown at the top. X is a function of t, and y is also a function of t, the same parameter. Then we can plot x against y. The data table on the following slide was produced by using parametric equations for the cycloid. If you are already familiar with parametric equations, that might have seemed like a grossly inadequate description. However, a thorough discussion of parametric equations is better reserved for another lesson. If you don't know much about parametric equations, or have never even seen them before, don't worry. For our purposes here, just realize that I take the value of t and plug it into the expressions for both x and y. The last column is the third order interpolating polynomial we found earlier. Notice again that it passes exactly through the original y values, seen here in the red boxes. The difference is subtle, but you can distinguish a small deviation in the blue and orange lines in between the red dots. This is a visual representation of how close our interpolating polynomial is to the true data. In this case, we knew the exact data values because they were based off a known curve. We don't always have this luxury. However, we can test numerical methods on known curves to see how well they perform. Then we can choose the best methods on data whose underlying function is unknown. This will give us confidence that we are getting the best results possible, even if we have no basis of comparison. That was a general statement. Of course, some numerical methods are better suited to specific situations than others, so I cannot make a blanket statement that one way is always the best. At any rate, we are starting to acquire a decent amount of tools in our mathematical toolbox. There are still many more to explore, so I hope you'll stick around for those too. Let me know in the comments below if you have any questions, or if there's a request of something you would like to learn in a future lesson. I appreciate your support. Until next time.